Hey guys, welcome to Thermodynamics video 10. In this video, as the title suggests, we're going to be taking a look at a thermodynamic process called an adiabatic process. In addition, we're going to do some comparisons between the thermodynamic processes we've looked at so far from the vantage point of the first law of thermodynamics and the ideal gas law. In subsequent videos, we'll be taking a look at how we can construct a cycle, and then we'll take a look at entropy and a whole aspect of these different processes that we have not considered yet. Let's get into it. So the challenge from the last video was to figure out what would happen in a process in which I had a very well insulated container or a very well isolated container. So there was some sort of an expansion and there was no heat exchange, so Q was 0. Well, in this case, if there's an expansion or compression, we're going to say that there is the possibility of work being done, because according to what we discussed in the last video and the previous two, any change in volume results in work done. So great, there is work done. We know heat is 0, so that means that delta U has to correspond to the sign of W, or work. So in the expansion, the work done on the gas is negative, so delta U must be negative. In a compression, the work done on the gas is positive, and so delta U would have to be positive, because Q is 0. So what this means is that there's some sort of change in the system that is resulting in a drop or an increase in temperature, and therefore a change in the internal energy. Now, if you look back to the isothermal video, this was the other process that we had listed alongside it, and we were using to learn the isothermal process by comparison. So in a sense, the isothermal process can almost be considered as the opposite of the adiabatic process, or the opposite extreme of the adiabatic process. So in this isothermal process that we looked at before, we said that it happened at a rate that was slow enough so that I could continuously be adding heat into the system or removing heat into the system for a compression so that the temperature never changed. Whereas in this process, known as the adiabatic process, we see that there is no heat exchange, and so the result is such that I have a drop in temperature. So it has a very similar PV shape, but it does not occur along a perfectly hyperbolic line. In other words, the function ends up dropping proportionately more so that the temperature is not held constant. Delta U is not constant, and there is a Q of 0. So one way we can look at the difference between an isothermal and an adiabatic process is that an isothermal process can be said, obviously here we're talking about a monatomic ideal gas, that an isothermal process can occur if it occurs very slowly. In other words, I have time to keep putting heat in at the rate that is needed to match the expansion, preventing a temperature drop. Whereas an adiabatic process, if we don't want to look at it as an insulated or an isolated process, we can also look at it as an extremely rapid process. In other words, we have this rapid volume expansion, and we have therefore a drop in the temperature because there is not enough time to quickly add heat to the system to prevent this from happening. Now, the rate of the heat transfer into or out of the system really does change the kind of thermodynamic process, whether it's isothermal or adiabatic. But what we're going to see later on in some other videos is an entropy is another way that we can map what's happening in these systems and take a look at how we can describe the systems from an entropic standpoint or an entropy standpoint. So now let's put all four processes on the same PV diagram so that we can compare them. Let's start all of them at the same pressure volume state and therefore the same temperature state. So they all start here at P1 and V1 and also T1, which could be calculated using the ideal gas law. We'd see that the isobaric expansion to V2 occurs with no change in pressure. The isochoric change, if you will, because it's not an expansion, would drop to a new p-value but have no change in volume. Now the isothermal process expands to V2, and it does so at the same temperature, and the pressure drops proportionately therefore, and this occurs because of heat exchange. And the adiabatic process has an expansion that is a lot steeper than the isothermal process. Now if it's insulated, isolated, or happening very rapidly, it expands to V2 with a more than proportional drop in P, or pressure, to result in a temperature change because there's no heat flow. So the next question is to determine which process, if they're all starting at the same volume and the same pressure and ending all at the same volume but different pressures, which process occurs with the most work done. Pause the video and try to determine that for yourself first. Well, it's clear that the isochoric process has no work done, so it's the least by default, and we'll remove it from this discussion for now. Now, if we take a look at the isobaric process, the isothermal and the adiabatic, the way that we can compare the amount of work done would be to determine which of them has the most area under the equivalent function, because we established before that that is one way to calculate the amount of work done. And we can see that the isobaric process has the most work done in this case because it has the greatest area. Next would be the isothermal, and finally the adiabatic with the least amount of work done. Now we could integrate the isothermal and the adiabatic processes in order to calculate the exact amount of work done by doing an integration, or we could just estimate it. So let's estimate in these cases just to save some time. We'll put a straight line from A to B in each case, and we can see that the trapezoid is a little larger in the isothermal process case, just to kind of visualize this all together. It's at this point in comparing the different thermodynamic processes that students want to say, well, it looks like isobaric's the best process because it gets the most work done. But remember, science tries not to have an opinion. It tries to look only objectively at the facts. But then what's leading us to sort of intuitively think best or worst? Well, I think it has to do with what we discussed when we looked at the rationale for even learning a PV diagram. What the heck is the point? And remember, we came to the conclusion that it was important to look at efficiency, and it was helpful to have an objective way to determine what sort of efficiency was going to occur. In other words, how much energy am I putting in to how much work am I getting out of these systems? So that is what I think we're trying to say, is which of these processes is the most efficient. Well, we're not really ready to compare that yet because we've only looked at these individual processes each on their own. We haven't looked at them as a cycle yet. And so in the next video, we're going to take a look at how we would put these processes together to get what we call a thermodynamic cycle. And then we can start to really look at efficiency, where we see overall as this heat engine or this refrigerator that I've referred to several times, we can actually compare which would be the theoretically most efficient combination of processes and which one is maybe the least efficient. And it all depends on the cycle rather than the individual processes. So as always, I leave you with a challenge. I want you to try to come up with a cycle on a PV diagram. Now, a cycle means that I'm returning to some point over and over again as I cycle through the many different processes. So we're going to start with a point on a PV diagram, and I need to figure out what combination of processes can I have and what direction for each process to return to that state. So hopefully you're seeing that you probably need at least 3 processes, but probably 4 in order to cycle back to this original state. Go ahead and try to do that and to describe what that would look like in terms of the piston and the cylinder. And when we come back for the next video, we'll finally take a look at a thermodynamic cycle.